Okay. Did I push the button? I must have. Okay. First, discussion of instrumental analysis, right? So you read about signals and signal processing and things, and the measurement up here on top, that's just right. Your machine that you're using, you've already had some experience yesterday pushing buttons and things, and you get a lot of signals and measurements depending on what the machine is, but that's what we're after, right? But if you break it down, it really breaks down into two parts. One is what you're after, really, the signal, right? But you can never have a pure signal. You're always going to measure some noise with it. And that's really what complicates things. And that's really why you got to pay the big bucks, is to reduce that noise as much as possible. All right? So that noise is really what we're going to focus on. And the whole rest of the semester will be the signal, but getting gas chromatography or liquid chromatography or spectroscopy, whatever the case is. But let's just focus on noise for a little bit and how manufacturers have learned over time to get rid of it. And when it comes down to it, it really comes down to a third grade science fair project. But we'll get to that. Okay, so noise. Seems like there's two types. You can be it can be from your chemical system itself. All right, there could be problems right there. Your chemical system. You could have interference, or you could have other things that are not helping getting your measurement, right? But the one that we can, and that's just knowing what you're doing, and sometimes you're just stuck with it. But environmental is the one that we can work on. Environmental is the type of noise that we really can influence and try to reduce. Okay. So this environmental noise, there's several types of them. Okay. I want to talk about thermal noise first, because in these instruments you have all these electronics, right? And it's a lot better than it was before. I remember, geez, I'm old, but I remember when these first starting to work on, well, they've had computers for a while, but when they're first really starting to get powerful and useful, you had to have them in these air-conditioned rooms. Everything had to be nice and cool. Well, that's because of thermal noise. So you had to make things colder to reduce the noise. So that's kind of the situation here. Colder, and then you'd reduce that thermal noise. But that's that's a lot better now. The electronics we have now is a lot better. But still, you can't remove it completely. Okay. And then we have next one I want to mention was shot noise. Now, shot noise, I can call these noises, I guess. This really isn't going to make much sense until we talk about it. Shot noise is something from like the detector, and you just can't stop these false signals from coming. And PMT is probably the prime example. What that stands for is photo multiplier tube. Don't worry about it, because we're going to talk about that later. But it's just another type of noise that comes from detectors. And some detectors are much, much worse than others. PMT is one of them. And we have flicker noise. Inside the workings of a lot of instruments, things are very often collected at certain frequencies. And if you can reduce the frequency, you can reduce the flicker noise. And so this is kind of a broad idea, but if you can reduce the frequency, you can reduce the flicker noise. But that's why sometimes in some instruments, if you really dig into their guts, like I had to once on our UV vis that broke down, and there's something they call a chopper. And if you put a little piece of paper in where the cuvette goes, you see the light, But that light is actually, if you could really have a fast eye, you could see it's actually flickering. Well, what they do is they have this, all they have is a spinning disc with little holes in it, and it's spinning in front of the light source. So the light's really going across at a certain frequency. So that's what they're messing with. They're messing with trying to reduce flicker noise and get it into a nice frequency range. But it's one of the things that they're trying to work with. And then the last one is environmental noise. This is a biggie. But it's one of the environmental noise. What is that? I mean, noise coming from the environment. Well, all these instruments, there's a gazillion wires in here. Every single wire can act like an antenna. And well, what does an antenna do? It picks up all these radio frequencies, TV frequencies, all this stuff. It acts like an antenna. It picks up these signals that aren't even supposed to be picked up. They're supposed to be running, right? Solely your signal. This is all you want going through your wire, but these wires, they pick up a lot of, they act like an antenna. And that's kind of what environmental noise is. Things that are acting like an antenna. So the one that we can really talk about and focus on the most is that environmental noise, because, well, shot noise depends on the detector, PMT. We'll talk about that later. Thermal noise, well, let's talk to those physicists and everyone else who's making resistors and diodes and everything else. That's as good as we can get right now. Not much we can do there. Flicker noise, we pretty much have to tear apart an instrument and look at choppers. Well, not much we can talk about there. But environmental, one of the biggest areas we can really focus in on him and give you some insights into that type of noise. So let's take a closer look at environmental noise and how you get rid of it. So I think it'd be good first to kind of witness and experience this stuff. So that's what I have over here. Okay, I don't want to skip anything. So, whoop. Oh, I don't want to talk about that. What is this one, the big one, called? That's the, starts with the O. That's the oscilloscope. All right. This one is our voltmeter. And you're going to be playing around with this one more in the laboratory electronics lab. And I don't know. Fun is subjective, right? But I think the laboratory electronics lab is going to be fun. I just wrote it. But I designed it so that, because following little, if you ever had physics where you had to follow an electronics diagram, like little resistor had a little symbol, remember, it's that squiggly thing? Okay, so there's a couple different electronic schematics, and that's all I give you. And then I give you the parts, and you need to build a little circuit, and if it's working, little lights blink and all that kind of stuff. But these schematics are not that easy to follow, especially when you start throwing in capacitors and some potentiostats. It's not that easy. But if you can see a picture of it, you just put it where it is. So I've got a picture there, but if you have to look at the picture, you'll get penalized 5 points or something. So I don't know. I think it was fun for my kids when they did it. But okay. Penalized. Okay, so voltmeter. What good is it for? Well, Alice uses all your batteries, and she gives you this one. Well, is it any good? Well, you can use a voltmeter for it. These voltmeters, I don't know if you've seen them. Walmart has them for a couple bucks, right? So when you play with a voltmeter, there's a V for volts, right? But then you have a flat line, and then you have a squiggly line. And it's not going to work unless you have it on the right one. So the flat line means what? The squiggly line means what? Does anybody know? If the voltage is changing over time, it's going to be the squiggly one. It's like what's coming out of the electric sockets. If the voltage isn't changing over time, it's a flat line. So they call it DC and AC. DC is the flat line. So which one is a 9-volt battery? Would this be DC or AC? What would you guess? Is the voltage changing over time? Well, if you wait a really, really, really long time, it's dying on you. But the point is, it's supposed to be staying at 9 volts all the time. So make sure you have this over on the DC part. And it's got all these little scales. So this is a cheapo version. expensive ones, you just put it on the V straight line and it'll auto range itself. But this one, you know that's 9 volts, so let's put it on maybe the 20. And, all right, red goes to positive, black goes to negative. All right, hold that up, Sandy. You can hold that voltmeter up so people can see what and the voltage is 9.2. They give you a little extra on these new batteries, right? So that way they can make the expiration date 20 years from now instead of 5. Okay, so that's good. Oh, what if I would, hold it up again. What if I would switch these probes around and connect the black to positive and the red to negative? What happens to this guy? Yeah, it just reads the opposite, hopefully. Right? Yeah. Okay, so what else can you do with a voltmeter? Right. A fuse or a light bulb, right? Is it burned out or not? Oh, right, you could screw it in the socket, but why? You could use a voltmeter. But you wouldn't put it on volts to find out if this guy's burned out or not. You put it on what? Someone said it. Ah, you're close. Ohms. Ohms. Put it on the ohms. You're going to measure resistance. And the trick to it is because if there's no resistance, can you hold that up again? If there's no resistance, in other words, touch metal to metal, what does it read? Close to 0 or something, doesn't it? But it's bouncing around. You get a reading. Okay? So if this is, they also call this a short circuit, but well, there's no resistance there, essentially. It's just metal to metal. So if I do the same thing when it's wide open, circuit's broken, now it reads, yeah, but it's infinity for that thing. It's just, that's its overload. Yeah, it's not even bouncing around, so it's overload. So contact, no contact. So with the bulb, the trick is just knowing where the wire's connected. One wire's connected to the very center. Where's the other one? Yeah, this guy. So you connect him. It doesn't matter which probe goes where. Then the other one to the end. Is this bulb good? Yeah? Okay, so this bulb's good. Okay. So that's easy. You can do the same thing with fuses. Fuses are the best way. This is the only way to check fuses. You know those paper ones, special ones in cars and things? Okay. Here's a trick question. What's this? You're starting to see these little lights everywhere now. How do I get them out of there? LED. LED, yeah. Do they burn out? Sorry. Do they burn out? Yeah, they don't get hot and they're super efficient. But can they burn out? You look at that, Sandy. See, you see the little plus-minus probes, right? And there it is. There's a little gap there. Can you see a little gap? Well, if you have a bulb and the filament breaks, right, it isn't going to work. So this guy burned out. You saw me just take him out of the bag. Is he burned out already? Can't be, right? Let's try this. One on one side, one on the other. Anything happen? No. It's a diode. It's a piece of semiconductor material. This is chem, how this thing works, right? But yeah, it's not a filament in there. It's extremely efficient. All the energy in these incandescent bulbs, pretty much, yeah, you get a little bit of light, but it all goes to, heat. Yeah, it all goes to heat. All right, we'll pass it around so people can see a little gap in there. Okay. That's about it. What does an oscilloscope measure? Okay, so here's I talked to you about the voltmeter. Spend about $1,000 more, do all the exact same stuff with this. It looks bigger and all these little nice buttons and everything. And to this day, I really don't know how to use one. All I do is, I'm just being honest, like everybody else. All they do is they push these buttons and rotate them until they get what they want. That's pretty much all you do. Okay. But anyway, so I did that. I don't know if someone was here early, they saw me messing with it, but okay. So what does this measure? Same thing. He measures volts, but with respect to time. How voltage changes over time. So you have volts going up and down here, and then time going this way. Okay. So if I put an oscilloscope with a battery, all right, let's see. It should read flat line or a squiggly line? Flat, right? Oh, that's off scale. Let's see. See what I'm doing? Just got to play around with this until I get it to work. Where's position? I need it. Oh, there it is. Let's see. So flat line. DC volts. Okay. And if we would have been careful, we would have seen it jump up 9 volts. If we could, watch the boxes and see what the voltage is for division and things, it would have jumped up 9 volts. Okay. Function generator. Ooh, I do need another one. What's a function generator? Okay, I don't know if you can see, but on this is what they call a function generator. And there's all these little types of signals it's going to send out. Square, sinusoidal, triangular. Okay, that's just how the voltage is changing over time. What does sound like? I need some help here. You have to hold that. I got to bring it closer though. All right. Oh, I need some more. Make it louder. It is louder. I gotta make it where you can hear it. What is our frequency range? Oh, I don't need that one. I could just use one of these. This will be easier, Emily. I'll use this one. Then I don't need to worry about any connections. I have a little speaker on here. Oh, he's broken. Son of a buck. I gotta resolder that. Oh, he's broken. No. Maybe I'm on the wrong one. Let's try this one. Okay, we're out of our hearing range. A dog could hear this. What this is 10,000. So it's about, what, 10,000? About 18,000 hertz. Frequency's way too high for your hearing. But bring it down. Right? So are your ears as sensitive to all frequencies? Right, some of these sounds get much more nauseating than others. Well, that's way too low. The speaker hardly even responds to it. Right? But anyway, so this is what your ear hears, but what kind of electronic signals actually go into this thing, right? All we need to do is connect them into here. Closer. Play around with the buttons till we get what we want. There. Okay, and then you can play around with this. So this is what that's what the signal looks like. That's coming from the function generator, and that's what you heard. So if you change the frequency, what's going to happen to this? If I change the frequency of this thing, here it is. Yeah, how is frequency change? Is it going to go this way, or is it going to get higher? So you can see it better. Right. This is decreasing or increasing the frequency? Decreasing it. Right. Here's increasing it. What if I was going to mess with the amplitude? Make it louder or softer? That's making it softer. Yeah, here's me, as loud as it can get. Okay, so that's a nice signal. But this is top of the line in electronics. The environmental noise is effectively blocked here. Look how beautiful that is. It's a straight line. Noise is noise, right? That's noise. There's no noise here. So let's get a more complicated signal and see if we can start seeing some noise. Let's see. I'm going to have to use this guy because my other one's broken. Hopefully he's going to work. Now, no one's in the choir. Can you hold that? No one's in the choir here, right? I had one dude who's in the choir because you've heard, if you were in perfect, you heard the sound, perfect frequency, perfect tune, we should see a little, right, a single sinusoidal wave there at the right frequency if you're right in. Oh, where is it? Here it is. But I can't sing, so I'm not going to try. But I can talk. What's talking sound like? Go ahead and talk into that thing. And I can talk in if you have nothing to say here. Put one into this one into that one. Oh, he's broken too. Oh no. Well, I'll have to hold it. I gotta really lower the, because it's a very weak signal, so I really need to lower the. See, can you see the signal now? I really need to lower the voltage and the frequency in order for you to see the signal. And it's not so easy to see, but it's there. It's there. But it's getting to be so weak that now the noise is starting to come into play. But my voice is there. It'd be better if we could put in, here it is. Man, you're not going to be able to hear my Doppler effect demo now. My speakers are broken. That's okay. Okay, put it into the headphone slot. Now the signal it usually goes to your headphone. It's coming out here, right? Now we're getting more into a real life type of signal here, something that's getting kind of complicated. Here it is. Okay, connect him to the, it's coming out of this radio here. See, now we're getting into something that's looking, that's too much. Look at that. That's a real signal. And if you increase the frequency, the volume, all right? So you can see this looks like noise, but that's the real signal. So processing this kind of stuff is complicated, but you gotta somehow just block the noise in the first place. Then you don't need to worry about it. But all this stuff really is blocking the noise. What does the noise look like? Let's see if I can show you the noise. Here's just a copper wire, right? There's miles of this stuff in your typical machine. see it? It's covering the whole screen, but I can't get it. See? So whatever's something, see, these are wires too. Wire. Put it on there. Something's different between these wires and the wires in here and this bare wire. Right? Something's different. What's different? Okay, so we've done all these here. A BNC cable. So if I do the same thing, wire, bare wire, right? Pretty much the same length, and the copper wire's inside there, right? But it's surrounded by this plastic thing. Then it's surrounded by a whole bunch of copper wire, then this black plastic thing. Do the same thing. Right? Big difference. So whatever they're doing here works. It's blocking the environmental noise. What is that environmental noise? Right? What is the environmental noise here? What is this thing picking up? Yeah, now I'm touching it, so now I'm part of the antenna. It could be, who knows, whatever station this is. All right? But it's all the different radio frequencies coming through. There's a lot of radio noise coming from the electric sockets. So it's just a bunch of noise. So somehow this guy's blocking it, and you can kind of see how. Right? Right? How does he block the noise? Let's show you the 3rd grade science fair project. Literally is. I had my son, he has his 3rd grade, had to do a science fair project. So I said, all right, what can block a radio wave? Because that's essentially what we need to do. And that's essentially what this thing is doing. It's blocking a radio wave. All this. So the idea is take this radio, stick it anywhere. If I can block the radio signal coming to this, what would it sound like? Nothing. Yeah, right? So he stuck it in plastic bags, he stuck it in drawers, he stuck it underwater, he's put it in all these different places, right? And he found some things that actually worked and found a trend, and he made a poster of it. So then he presents it at Linton Elementary. Who won the science fair project? The volcano! Yes! Every single year, the volcano wins. I have no idea why. He gets published in the Journal of Chemical Education. Every single university, every single college has his article in the Journal of Chemical Education. It's that big of a deal. But he can't win a 3rd grade science fair project. Right? Those judges had no clue. They thought it was a trick. They had to have, right? I don't know. But anyway, what did he find out? What can block a radio wave? Metal. Yeah. All right. All right. Make it louder. Does that help? Right? How about nauseating? How about jab a bunch of holes in there? Your pen. And get some more in the middle there. Oh, shoot! Too much. Can you need some tape? Well, okay. What time is it? Okay. Now will it work? Kathleen, now will it work? Huh? Look at that. I'm not even close to covering it up. It's already blocking it. The answer lies in that darn microwave oven. You've been staring at it every time you put in popcorn. The little holes, right? Those little holes on that microwave oven door, how big are they? They're little, right? But how big is a microwave? Bigger than the hole. It's actually 1 centimeter. 1 centimeter is the size of a microwave. So if you have a gap in your microwave that's about this size, microwaves are leaking out. And just, right, Alice? Tell them.
His new microwave, it had like a big leak on the top, and then ours over here has a leak like in the corner of the door.
Because I got a new toy, microwave leak detector. And I was running it around there, and right by the door. That's a horrible spot every time you grab it. Right? So how big is a radio wave? Huge, right? Orders of maybe 10, 20 yards. AM is even worse. AM's like hundreds of yards. Should it work? Yeah, I mean, this is a lot smaller than a 10 yards, right? The little holes. You got it. This is hard to do, though. Oh, shoot. I can't get this one to work. You really got to push down and make a good contact. Otherwise, that circle just doesn't work so well. But this one is better. Okay. So what you need, make sure you do this. Draw a depiction of a BNC cable. So you got to draw your center connector. Like how does this thing work? How does a BNC cable work? Right? How does it work? Your signal is running through that little copper wire. So what's doing the blocking? Only this stuff, right? Yeah, the other copper. Now what's the purpose of this hunk of plastic then? You got to separate them. Otherwise, if this surrounding copper touched that one, it becomes part of the antenna, right? Part of the conductor. So pass it around, take a look at it. So make sure you can draw a picture of it and explain how the darn thing works. Fix these guys. Both of them are broken. That sucks.